Hello and welcome to my presentation. I'm Susana Proença and I came from Portugal to Netherlands. I'm doing my PhD in the Institute for Risk Assessment Sciences in Utrecht, and my supervisor is Linke Kramer. And my focus within the INTRI project is the in vitro and in vivo biokinetics. And so throughout this presentation, I'll show and I will highlight the importance of these kinetics in a chemical risk assessment, but I will also try to show a practical example how to do this integrated approach, especially within the INTRI project. So we'll start really in the fundamental of toxicology. The dose makes the poison, as Paracelsus said. But this paradigm is not as simple as it seems, because what is a dose and actually how does this dose relate to the effect? And so in the beginning, we would connect the external dose, for example, how much you ingest, to the effect of the individual. But as toxicology evolves and we get more models to test it and gets more mechanistic, we actually know there's several steps in between. So the compound that ingests, for example, needs to be absorbed, and then once it's in plasma, it gets distributed into several organs. And then even within the tissue, only a fraction of the compound will actually connect to the target molecule and causes its effect. And this fraction is what we call biological effective dose, or BET. And this is the one that will actually start the adverse outcome pathway. But in vitro, and when we're using more and more in vitro for toxicology assessment, we traditionally extrapolate the medium concentration to what we had to the medium, which is the nominal concentration. We extrapolate that to what's in blood directly. But we know now that's not necessarily accurate, actually, because the in vitro system also has distribution. Within, so the compound can bind to protein, it can evaporate, bind to plastic, and also the cells might even dilute the compound in the sense that the more cells you have, the less compound will be available for each cell to uptake. And again, even within the cell, the compound might bind to a lot of things besides the target molecule, because we tend to think cells are this empty space with just a few molecules around, and actually are really crowded. And the compounds can bind to lipids and proteins and to DNA. And so the first part of my PhD was actually seeing in literature the knowledge that is available for these different distribution processes. And I summarized the distribution processes that are described here in this figure. And so we can see, for example, so the compound, once it's in medium, it can bind to elements of the serum. So, for example, your protein and lipid, it can evaporate, it can get abiotically degraded. So even without the cells, it gets degraded, binds to plastic. For example, extracellular matrix sometimes might delay the diffusion of the compound. We still don't know if it's significant. Some compounds really like to stay in membrane, or other compounds actually have very low permeability. And so actually membrane is also a compartment on itself. And once the chemical is within the cell, it can bind to lipids of the cells. This is agglomerated of all lipids of cells, or the agglomeration of all proteins in the cell, and eventually can be metabolized. And by knowing these different distribution processes, we can understand there's different dose metrics that we can use for extrapolation. And actually, it depends which one is better or is a better proxy for bad. It actually depends on the chemical, on its mechanism of toxicity. So, for example, we can take into account the concentrations within cells, both bound and unbound chemicals that are reactive, because they will react to everything. But for example, chemical that will interact with intracellular receptor, then you need to take into account what is freely available within the cell. And then for compounds, sometimes they don't really need to enter the cell. They might just bind to membrane receptors. And in this case, for example, you can take into account what is freely available in medium. I do note here that, for example, what is free in cells and free in medium, a lot of times is actually the same concentration if the system is in equilibrium. But this doesn't happen always, because there's metabolism, there's efflux transport, for example. But those metrics are important to take into account, because they do differ the proportion with the nominal concentration changes with the compound and with experimental conditions. So that's why nominal concentration sometimes is not the best point of departure for extrapolation. And so, acknowledging all these distribution processes, several authors in the last 20 years have developed models, in silico models that predict or at least simulate these distribution processes. Sometimes they focus on one chemical specific, or sometimes it's a generic compound. This is quite a complex image. And I would say, like, if you want to know more about this, hopefully the paper is out in January, and then you can read more about the models. But here I try to simplify and focus on two differences that I see in these models that are important for the practical example I'll give. So in this case, it's the way we model the distribution processes. So it can be either modeled as a partition, and this means we assume once the chemical phosphate is in medium, it binds immediately to plastic. It's a matter of seconds, so we only need the partition coefficient. But for other processes, actually, sometimes it's a bit slower, the process, and then we need to have a rate and integrate it in the differential equation. And these processes are slow because they depend on diffusion, or because they depend on reactive enzymatic reactions. But the point is to decide whether we model processes as a rate or partition depends, of course, on how slow the process is, but it's also a relative matter. Depends how slow it is relative to the window of exposure. Because if you test for 24 hours or longer, sometimes a lot of processes, even if they take a bit of time, it might not be such a bad assumption to consider partition. But it also depends if the speed of the process will limit the speed of other processes, for example, such as metabolism. And then we go to the another difference that we see between the models. So it's the way they parameterize, so the way they give the partition coefficient and the way they derive their rate. So a few models, for example, use directly from literature experimentally obtained parameters, for example, your partition to albumin. Other models fit the parameters directly to experimental data. And in this case, sometimes there are parameters that are an agglomerated of parameters. For example, your rate of uptake into cells actually considers also the accumulation within the cell. And then other models use quantitative structure property relationships. So these models take into account the physical chemical properties of the compound to predict, for example, the rate into permeability or the partition into albumin. And for these distribution processes, a lot of the QSPRs are log-QW based, so partition octanol water, which is a proxy for lipophilicity. And they are suited for neutral compounds mostly. But once you start to have polar, neutral, and ionized compounds, you need more complex QSPRs. Some are, for example, polyparameter linear free energy relationships, and these are still relatively simple, but then they take descriptors that might be characterized by the polar compounds, for example. And I'll show an example to make it a bit more practical. So this is a paper from Hennenberg 2019. So usually we consider that the compound that's within the cell binds to lipid and to protein. But then we have QSPRs for serum albumin, so that's a protein, and to structural protein, and we have QSPRs for storage lipids and for membrane lipids. And if we consider that all the partition for lipids within the cell can be predicted by the storage lipids or by membrane lipids, we see here there's actually quite a bit of a difference. And you have to take into account these three compounds are acid compounds, so they usually negatively charge. And we see actually that they tend to actually bind more to lipids if we consider the partition is like a membrane lipid. And this is because membrane lipids are overall better to solubilize ionized and polar compounds than storage lipids. Storage lipids have very strong affinities to neutral compounds. And the same for albumin. Actually, albumin has much higher affinity to acidic compounds than the structural protein would have. So again, you see that if we consider all binding to protein can be simulated by structural protein, actually there's much less binding than if we consider it's albumin. And taking this paper and other papers in account, we actually made a small scheme of the best QSPRs that can be used depending on the compound. So if it's neutral, for example, then you can use mostly log-QW, but then as the compound gets polar, or if it's ionized, then you need to use more complex QSPRs, as I indicated. And here is a bit of an example of these models and the models that use QSPRs. And we see chemicals of different physical properties. You can see, for example, ibuprofen is mediumly lipophilic. It is a acidic compound. And we see that it actually binds quite strongly to serum. Caffeine, it's less lipophilic. It doesn't have a lot of binding. Triclosan has a lot of binding to plastic, but once you add the serum, this binding decreases because mostly it's bound to serum. Naphthalene is a volatile compound, and this is actually very complicated to model volatile compounds. Because actually, so in microtetra plates, they are not completely closed systems. So there's a constant flow of air coming in and out. So if the compound is evaporating, it actually continues to evaporate till there's no chemical left. And this can cause not just the loss of compound, but contamination between wells. Then you also see for diphenhydramine and diethyl phthalate, they're actually quite similar. They're semi-lipophilic compounds. But you take into account that not a lot of these models take into account ionization. This is something to look in the future, and takes me to the take-home messages from this review. So these models, in silico models, especially the general ones that use KSPRs, can be very relevant to improve in vitro testing because they can allow you to understand better the exposure of compounds in these systems, and sometimes to understand when there might be problems. Or for example, if you're using concentrations because you saw in another paper, you need to take into account the in vitro conditions. And this is also important for volatile compounds, as I said. The models might signalize if the compound is going to evaporate quite significantly, and then you should not test in a normal microtetra plate, for example. Then you should use closed systems. And but overall, these models, although they have been improving a lot in last years, we need more experimental validation, and especially for ionized compounds and for non-standard exposure conditions. So for example, very, very low exposure conditions, or when there's a withdrawal period, meaning you expose the cells to compound and then you stop exposing for a few days. So how is the compound being released? And this is also a very important takeaway messages for this new in vitro system. So we really need to take into account the kinetics. For example, organoids on a ship, sometimes they're characterized by having very small volume per number of cells comparing to a standard in vitro model. And they also have higher polymer surface area exposed to the medium and to the chemical. And this can result in very high losses of compounds, especially lipophilic compounds. And because a lot of validation models sometimes passes by through toxicity testing or metabolization, this needs to be taken into account. And there we go to the practical aspect of it. So this is the case study we chose, is to test